to his personal account. So even though it may be little, imagine the number of such transactions banks go through, right? And I have an example for that. So it looks like a non-avoidable problem, right? So how do banks handle this in a more genuine way? So he was caught, and that's how this became more popular. So how should banks handle it, and how they are handling it now? What they'll do is, if it is below 0.5 cents, they will kind of truncate it. For example, in this case, they will pay the customer only 456.34 cents. If it's say 0.348, they will pay the customer 456.35 cents. So on average, it balances out. In some certain cases, the customer loses what? Around 0.5 cents at the worst case, right? Because if it comes below, if it's either 34, 1, 2, 3, 4, he loses about 0.5 cents, right? And certain cases, the bank loses 0.5 cents, because if it is something like 3, 4, 6, they have to pay 35 cents, right? So they lose some, at the worst case, 0.5 cents. Okay? So it's a give and take. Sometimes in some transactions you lose 0.5 cents, in some transactions you gain 0.5 cents. So on average it balances out, both for the customers put together overall and for the bank. Okay? So that's how it should be handled, and most of the time that's how they handle it. But someone misused it, and what he did was, when he developed the software, he kind of truncated it. So even if it came to 0.346 or even 0.349, he let the program to pay the customer only this much. So that remaining 0.9 cents, everything got kind of forwarded to this one account. Okay? You see the attack here? You kind of, the basic thing is, instead of rounding it to the next closest digit, you kind of truncate it. And that's a small programming thing, right? Just one line piece of code, but it kind of can launch such a huge attack. So let's do this small numerical problem, and we can proceed further. Say a bank can do like 1,000 currency exchange transactions per day on a 5-day work week, 52 weeks per year. How could a programmer developing the code for the currency exchange could launch a salami attack and pocket money to his account, right? For how much money? So again, so we have 1,000 transactions per day. It's a 5-day work week, and you have 52 weeks per year, right? So find how many transactions are there per year. So it's going to be 1,000 times 5 times 52, right? Per day, per week, per year. So just multiply all this. So you have basically that many transactions. Isn't it? Okay. So if you multiply these two, this is what? 20, 60. So this is 20, 60. That many transactions per year. So now you have to find out how much you can gain at most from each transaction. How much a person can gain from each transaction if he launches a salami attack? 0.5 cents, right? That's the maximum he can gain. So 0.5 cents gain per transaction. So all you have to do is multiply this 2060 thing by 0.5 cents. So if you want to convert to dollars, it's going to be $0.005, right? So that will come out to be $1,300. Okay. So this is what he can really gain from per year. Okay. So that can pay for holiday vacation, right? So $1,300 per year.
So how many years was it before they caught him?
Huh?
So was it a year before they caught the person?
I think they what?
Like how long was he able to keep it?
I am not sure how long he was able. It happened sometime in the middle 80s.
Oh, that was a lot of money.
Huh?
That's a nice
Yeah.
little amount of money. Maybe
Right.
a year. Really.
Right.
$5 full-time pay. Brother, no.
Why this is Alright, so I don't know what happened to this. It should be smaller font and more information. It appears like this. Yeah, I'll try to see what it is, but let's go through this now. So now we are going to do what is called the arithmetic overflow attack. So this one and what we're going to see will require some architectural background, but not much. Alright, so if you work with say 8-bit quantities, right? So let's say this is the kind of size of some variable that you have. Okay, so you keep adding 1 to it, so it comes out to be something like this. You keep adding another 1, it comes out to be something like this. And keep going, you have something like this after a while. And then you add a 1, you get something like this, right? So if it is going to be expressed in kind of, so this is say an integer, okay? So let's consider 8-bit integer. If it's going to be expressed as, it depends now whether it is a signed integer or an unsigned integer. Are you clear of that, what it is? What is the difference? So everyone has noted down we have a quiz coming up on Wednesday. So in a signed integer, in this, what is the most significant bit? Can anyone tell what is the most significant bit? Left.
Yeah.
So this is the most significant bit and this is the least significant bit. Why we say so?
Determines the sign.
Determines what?
The sign.
Yeah, the most significant bit determines the sign if you want to represent integers. But why we call some bit, a particular bit as the most significant bit? Don't know? No? Okay. Again, we can represent things as exponent of 2, right? So let's say we want to represent 8-bit quantity, isn't it? So if I want to, so this bit position is having the largest weight. This bit position is having the lowest weight, right? So if I want to represent say something like 140, I make this to be 1, make this 0, 0, and what else? This is 140, isn't it? This accounting for 128 and then you are counting only 12, so this is 0, 0, then we have 136 with this, then 140. Everyone is comfortable with this? Converting from decimal to binary? Okay. So this one basically is weighing 128 out of this, right? Whereas this one weighs only 1 and 2 and so on. So that's how you distinguish which was the most significant bit and which is the least significant bit. So from that context, this is the most significant bit. So and this is the least significant bit. Okay. So in a signed integer representation, the most significant bit doesn't really store the weight. It stores as a sign. Okay. So you really have only 7 bits to play with. Right. Whereas if this is an unsigned case, then the most significant bit can store a weight, that largest weight value. Okay, so in this case it's 128. So it means you can really go further, because with a signed bit you can have to stop over here and it kind of rolls back, you will see quickly. But with this unsigned bit you can go further and you can have something like this, and then you can have something like this, and so on up to all ones. Right? So you can really go from what in terms of decimal values, you can go from this is 0, this is 1, this is 2, this is 127, this is 128, 129, 130, all the way to 255. Alright? So that's the kind of range of values you can go for unsigned integers. But now, even with this, what will happen? If you try to add another 1 to it, what will happen?
Overflow.
That's the overflow, because let's say you work only with the 8-bit quantity. Okay? So when you do one more addition, what happens? You have 1 added with 1, the carry, the sum is 0, carry of 1, this is 0, then carry 1, 0, 0, 0, 0, 0. So you have a carry to the left, but you have only 8 digits you can store things, and you have put all 8 zeros. So where will this 1 go? You have to drop it. Okay? So that's what we mean by overflow. Okay? So which means what? If you have a variable like I have in this program, although it may not be readable much, but let's say I have, say, same thing as I wrote here, this char num is, say, initially 0, and I keep incrementing it by 1, and after 256 increments, it goes back to 0. And then further increment, you'll again start from 1, 2, 3, and so on. Another 256 increments, it goes back to 0, and then 1, 2, 3, and so on. Okay? So that's what it does if it is an unsigned integer. If it is a signed integer, what happens? If it is a signed integer, the range of values is from what? If it's an 8-bit quantity, in this case, the range is going to be from negative 2 to the 7 to 2 to the 7 minus 1. So, because with a signed bit, right, signed integer, you don't really have 8 bits to work with. As I said, you really have 7 bits, right? Because the most significant bit takes care of the sign. So, with that in mind, you really can have only this from negative 2 to 7 to 2 to 7 minus 1. Okay? So, let's see how it works. I hope someone can read from there, but let me do it this way. You write this?
Mm-hmm.
Okay, so if it is a signed thing, so now you're working on signed integers, so signed 8-bit integer. So with signed 8-bit integer, the value of the integer is normally determined like this, as I show over there. This is of course for 32-bit, which will come to that after this. In this 8-bit case, it is broken up like this. So I don't know if you put all this in architecture, but let me tell you. So the value of this integer is how much this other bits, other than the most significant bits, make up. And then what you do is, whatever their value is, okay, so whatever the value is, minus this is like what, really 128 if it was accounted as for read. Okay? But if it is a 0, this is really 0. If it is a 1, that's when you account the weight for and you say it is 128. Okay? So if it is a 0, the sign of the integer is really positive. If once it becomes a 1, the sign becomes negative. Okay? So let's do like some numbers. So if this is 0, right? So the sign is going to be 0, so the value, its weight is 0, okay? So the whole thing is 0, so 0 minus 0 is 0, okay? So if it was just all 8 zeros, okay, so let me write on the top, so it is x minus 0, so 0 minus 0 is actually, you can have plus 0. Now 0, 0, 0, 0, 0, 1, this together makes what? 1, right? This is just 1. Minus 0 is going to be plus 1. Then you have 0, 0, 0, 0, 1, 0. That's 2 minus 0, that is plus 2. So you can keep going all the way to 0, 1, 1, 1, 1, 1. This is going to be how much?
256.
127, right? So if you add all of this, 1 plus 2, 4, 8, 16, 32, 64. So 64 plus 32 plus 16 all the way to 1, add up it's 127. So it is 127 minus 0 is 127 plus 127. If you add one more, if you add 1 to this, what will happen? What will happen if you add 1 to it? This will become 0, 0, 0, 0, 0.
There'll be a 1 to carry?
1 with 1. The most significant bit becomes a 1. Right? So apply the same kind of formula. This 7 bits together make up what now? 0. And this is a 1 over here. So then it becomes 128. So this is negative 128. You see, if you start with all 8 zeros, it is 0. Then you increment by 1, it is plus 1. Increment again by 1, it is 2, and so on. It is okay up to 127. If you add another 1 to this 127 as a signed integer, 8-bit integer, it becomes negative 128. And that's what that program I have in the previous one shows you. And you add another 1 to it, it becomes what? 1, 0, 0, 0, 0, 1. And this is what? 1 minus 128. So this is 1 by itself, the 7 bits, and then this is 128. Right? So 1 minus 128 is negative 127. So all the way you go up to what? You can go up to 1, 1, 1, 1, 1, 1. So this is going to be what? 7 ones is again 127. 127 minus 128 is negative 1. Okay? So start with 0, 1, 2 up to 127, and then negative 128 all the way to negative 1. Right? So that's the range of integers you have. This is negative 128 to negative 1, then is 0, then 1, 2 up to 127. Right? So what we just now did is called what? 2's complement arithmetic. You're aware of all these terms, right? So as a programmer, you should know what is the size available for your variables. You cannot just blindly keep incrementing them because they will overflow. Right? So that's what is called arithmetic overflow problem. And someone can misuse it as an attack, but we'll see quickly what it is. But you understood the idea?
You said you have to keep track of the
You have to keep track of the size of your variable. Like if you're using a signed 8-bit integer, you cannot just keep adding, incrementing it. You have to really know when it can overflow and when it will wrap around. Okay? Because you see, if you add one more to 127, it doesn't become 128, it becomes negative 128. If you add another one, it becomes negative 127. If you add another one, it becomes negative 126, and so on becomes negative 1. So it's not really increasing the way you are expecting it to increase. So that's called the overflow. Is that clear? The same thing I have shown here as 32-bit integers. Right? So it increases in the signed case, it goes from 0 to, sorry, and the unsigned case. See, for example, even in the unsigned case, it increases from what? In the unsigned case, you don't have negative integers, right? So you go from 0, 1, 2 up to 2 to the power 8 minus 1, which is 255. So you go from 0, 1 up to 255. Right? 255 is what? All 8 ones. Right? So that is for unsigned. This is for unsigned. If it is signed, this is the range. Same way, if you have 32-bit quantities, the unsigned case goes from 0 to 2 to the 32 minus 1. Okay? And if you work with signed integers, that's similar to what I have here. You can see it goes from 0, 1 up to 2 to the 31 minus 1. And then it starts from negative 2 to 31. Like it starts from 0 to 127 and then has negative 128 and then goes down. If you work with, so this is what? This is 8-bit quantity, this is 2 to the 7 minus 1. And then this is what? Negative 2 to the 7. And then negative 2 to the 7. Minus 1 and so on, it becomes this is negative 1. So for 8-bit quantity, that's how it is. For 32-bit quantity, you have 0 to 2 to 31 minus 1 to the 31 and so on. So you should be able to find out when things will wrap around. So that's the whole idea behind this. Alright? Any question? So you have to just work out and be familiar with this decimal to binary conversion. Alright, so we are going to see how this could be misused as an attack. Okay? So someone has a kind of network connection program. So this is the kind of program that has this vulnerability. So we'll look at it and identify what it is. So it looks like a C code. Okay? So the program keeps track of the number of connection requests coming to it. Okay? So any customer can keep requesting for connection. The objective of this program is to make sure that it does not support more than 4 connection requests. So once 4 connection requests are granted, the subsequent connection request will be denied. Okay? So it is supposed to allow only 4 connection requests. And someone came up with a program to do that. Okay? Let's see that. So it's an unsigned integer connections, and you initialize to 0, and then you have basically code to do some networking thing. Now here, let's say the connection request has come just before this line. Okay? So it increments the number of connections. So a connection request has come, so it goes ahead and increments the variable connections. So then what it does is it checks whether the number of connections is less than 5. Remember I told you it's supposed to allow only 4 connection requests. So after the increment, it checks whether the number of connections is still less than 5. If it is still less than 5, it goes ahead and grants the access for that particular connection request. Otherwise, it says deny access. Right? Clear what this program does? So it gets a connection request, increments the connections variable, whatever its previous value was, it increments it by 1, and checks if it is less than 5. And if it is less than 5, it means it thinks that it can give at most 4 connection request grants, right? So since it's less than 5 now, it thinks it can grant that connection request, and then if it is greater than or equal to 5, it denies the connection request. So what is the vulnerability in this program that could be exploited? Is everything perfect, or anything kind of a loophole or something is there someone can exploit?
What if it's a negative?
Huh?
What if it is a negative?
You start with 0, right, and it's unsigned integer, so it cannot go negative. Okay, so, and let's say it could be a 32-bit quantity. Normally unsigned integers are 32-bit quantity, but if you want to keep it simple, you can analyze it as a 4-bit quantity, right? So let's analyze it as a 4-bit quantity and see what happens. If it is a 4-bit quantity, it starts with 0, 0, 0, 0. It's unsigned, so there's no signed bit and anything. Okay, so all the 4 bits can be used for the integer to represent its magnitude. So you do the first addition 0, 0, 1, right? So this is in decimal, it is what? 1, isn't it? So that happens, the first connection request is incremented from 0 to 1, 1 less than 5, the person is granted the access, right? So then the second request comes, you do another addition, this becomes 0, 0, 1, 0, which is number 2, then you grant the access again because 2 less than 5. Okay? So then it will be 3, and 3 is less than 5, grant the access. The fourth connection request comes, it will be 0, 1, 0, 0, you grant the access. The fifth connection request comes, you increment from 4 to 5, you check 5 less than 5. Is 5 less than 5?
No.
No. So you go to the else part and say deny access. So fifth connection request will be denied access. Okay? So what will be the new value of connections, that variable? It is 5 now, right? This is a new value of connections. Now let's say the sixth connection request comes. It will be incremented from 5 to 6, right? And you check whether 6 get less than 5, deny is false, so go to else part and deny access. What happens? You keep on requesting, you keep on sending the connection request, and after a while it becomes like this, right? You send the 7th request, 8th request, 9th request, and so on. You send the 15th request.
Syn attack.
Huh?
Syn attack.
Say again?
This is that the SYN attack. That's the name
No,
of
no,
it.
no, no. This is just to explain arithmetic overflow. After the 4th connection attempt, you are not supposed to request anything more, because let's say you requested the 5th attempt, or the 5th connection request, you are denied, right? So someone should know that they should not really try anymore. But an attacker knows the kind of vulnerability because it's unsigned integer connection, and he knows the structure of the code. Okay, there's a problem with this code, and we'll go through that. Okay, but with this code, this is what happens, right? You keep incrementing connections from 1, 2, 3, 4, then 5. Then the 6th connection request, you increment one more, and you check 6 less than 5, false. So you go to the else part and deny access. But the attacker keeps on requesting connections, and for every request, what happens? The connections variable keeps increasing, right? So it increases from 5 to 6, 7, 8, 9, it goes to 50. Then he makes a 16th connection request. When he makes a 16th connection request, what happens? You add a 1 to the connections, right? That's what you do. You do connections plus plus. You add a 1 to it, what happens? It becomes
0.
Right. It's an overflow now. This carry cannot be accommodated anywhere, so it comes back to 0. Right? So now connections is really 0. So it checks 0 less than 5, it grants the access. So it can really allow the 5th connection. Not only that, another connection request, it will be incremented from 0 to 1, it can allow a 6th connection request, and then 7th and so on. You see that? So this way someone can exploit it, even though in between they'll have a lot of connection failures. They can keep on trying by generating those fake connection requests, and after a while they can be successful. Right? So this is the vulnerability with this program as it is. So how to fix it?